So we're very pleased today to have Leonard Susskind from Stanford. He'll tell us about DSSYK infinity equals JT plus.
Okay, thank you, Edward. Good. All right, this is somewhat of a continuation of the previous talk I gave, although it's self-contained. It's about de Sitter space. DSSYK, what does that stand for? I'm not sure. Double-scaled SYK, and the infinity stands for temperature. And on the right-hand side is JT gravity, but the plus stands for plus cosmological constant. In other words, a version of JT gravity, which is de Sitter space, or some version of de Sitter space. We're going to talk about de Sitter space and the holographic principle. There are some basic principles that are important, but I think in order to get those basic principles really firm and to understand them completely, I feel the need personally to have concrete constructions that we can explore and try out these ideas. Some people are smart enough to be able to understand the basic principles without the concrete constructions. I don't think I am. Static patch holography is the framework for this talk. The holographic degrees of freedom, this is principle number one, the holographic degrees of freedom, to the extent that you can say that the holographic degrees of freedom live anywhere, I think it's appropriate to say that they live on a stretched horizon, a microscopic distance from the true horizon. So that will be principle number one. Number two, a boost Hamiltonian exists. We talked about this last time. And you can think of it as the right side Hamiltonian. Let's just, let me get my pointer here. Yeah, just a second. Yeah, the right side Hamiltonian minus the left side Hamiltonian, but you have to be careful. The right side and the left side Hamiltonian individually are somewhat singular. It's safest to think about the difference between the two of them, where the singularities cancel. So a boost Hamiltonian exists for the purpose of dynamics. Three, the static patch density matrix is maximally mixed. This already has become something of a standard. Well, I don't know if it's a standard assumption or not, but I will assume it. Equivalently, given that there is a Hamiltonian, we can say that the Boltzmann temperature, the temperature defining the density matrix, is infinite. Takes an infinite temperature to have a maximally mixed density matrix. Four, all of the symmetries of the holographic theory are gauge symmetries of the bulk. All of the symmetries of the quantum mechanics of the holographic theory are gauge symmetries of the bulk, and by the bulk I mean the static patch. All of those, I think, are fairly straightforward.
I have a question.
Yeah.
So when you say that T is infinity, doesn't that mean that T Boltzmann is infinity?
Yes.
You hear me?
Yes.
Doesn't that mean that beta goes to 0, and then how would you define the partition function?
Sorry, I don't know. What is the problem?
Beta goes to 0. If T goes to infinity, then beta goes to 0, right?
Yes, yes.
So then trace e to the minus beta h. How would you define that?
Just trace. Just trace.
Trace of identity.
Trace of anything, yeah. Trace of the identity.
Okay.
Right. Okay. The symmetries, let's remind ourselves what the symmetries are. The symmetries, which are the symmetries of the holographic theory, which become symmetries, which become gauge symmetries of the bulk. There are several of them. First of all, time, translation, and variance. Rotations which keep the center of the static patch, I call the center of the static patch the pode, as opposed to the antipode. Let me use that convention. The rotations which hold fixed the pole, any U1 symmetries that we may introduce that would correspond to a Maxwell sector in the static patch. C, P, and T if they happen to be symmetries, and most likely CPT. Hold on a second. I have to shut my phone. Okay, so CPT, all of those, I believe, should be thought of as gauge symmetries. We're not going to be talking about that very much. I just want to lay it out. The most confusing thing is the validity of the semi-classical limit. The semi-classical limit, I'll discuss what that means in a minute, but the semi-classical limit will take to mean quantum field theory in a fixed background. Now, the difficulty there, as emphasized by Edward, and I emphasized it last time I spoke, is that in order to match with the semi-classical limit, it's necessary to think about clocks. It's necessary to think about gauge fixing the various symmetries, and that's very puzzling and requires the actual physical construction of a clock, the physical construction of reference frames and so forth. And that is, in my opinion, what's making things very hard. And I'm going to largely ignore that for this talk. But because of it, it's rather difficult to know exactly how to compare a given holographic theory, a given proposal for a holographic theory with a semi-classical limit, so keep that in mind. Anyway, those are some principles. We would like to have a concrete realization to try out these principles. If we had a concrete realization, perhaps we could even build a clock. If we can build a clock, we may be able to understand better the semi-classical limit. The concrete realization that I'm going to talk about is double-scaled SYK at infinite temperature. Is it actually a representation of de Sitter space, of some sort of de Sitter space? I think it is. Most of my friends who I've talked to about that think that it isn't. We'll see. We'll find out eventually. Okay, to understand, in particular, to understand the JT version of this, the bulk description, I think it's best to start with 3D de Sitter space. Here's 3D de Sitter space. There's an angular variable alpha, and f of r is the usual de Sitter space, what is it called? Emblackening factor, 1 minus r squared over L squared. L is the radius of curvature of the de Sitter space. Here's a picture of a static patch. Here's the pole at the center. There's an angular variable alpha. There's a horizon to the static patch out here somewheres. And what we're going to do is think about dimensional reduction, in which the reduction takes place on the angular coordinate alpha. After the dimensional reduction, the metric simply is a time radial metric, and the angular direction is replaced by a dilaton field. The dilaton field in this case will be equal to r. Well, that's a solution of the JT equations. Dilaton field equal to the Schwarzschild coordinate r. Let's talk about the semi-classical limit now. By the semi-classical limit, I mean a limit in which the entropy goes to infinity. We may also want to impose some other restrictions to avoid huge amounts of energy, which can deform the space in some nasty way. But basically, entropy goes to infinity. That's what I will mean by the semi-classical limit. And as I discussed last time, I come back to this over and over again. You may get bored by my saying it over and over again. An extremely important issue is the separation of scales which takes place in this S equals infinity limit. I'm going to describe that again. I did last time. This time in the context of either 2+1 dimensional de Sitter space or in the JT version of it. The horizontal axis is the axis of scales. It goes from left to right. On the left is the minimum mass scales, and in fact, the largest length scales that we will ever consider. On the right is the largest mass scales. And what do I mean in this case? The left, the minimum energy scale, corresponds to an energy such that the wavelength associated with it is the de Sitter radius. So it's wavelengths which are as big as the whole space, and that corresponds to a energy scale which is the Hawking temperature. At the far right end is a maximum energy scale. In 4 dimensions, the maximum energy scale would roughly correspond to the energy of the biggest black hole that you can put into the de Sitter space. That would be a Nari black hole. Could even be a little bigger, maybe. But in the 2+1 dimensional case, it corresponds to an energy which would create an angular deficit equal to 2 pi and simply reduce the geometry to an infinitely thin sliver with as I said, with an angular deficit equal to 2 pi. That's the biggest energy that you can put in 2+1 dimensions. So there's the minimum energy scale, the maximum energy scale, and right in the middle, logarithmically, is a scale that I will call the microscale. In 4 dimensions, in the usual 4-dimensional theory, the microscale is the usual Planck scale. Here, I will just take it to be the geometric mean of the largest and smallest scales. That's the microscale. Logarithmically, it sits right between the maximum and minimum. And then we will be interested in something that I will call the string scale. We can also call it the chord scale. We'll discuss that thoroughly. And there's a region of scales which contains the microscale, the string, the chord scale, and contains a very broad variety of scales for which flat space is a good approximation, for which we don't have to worry about the curvature of the de Sitter space. If we think about things which are more massive than that, they'll have a severe back reaction on the geometry, and flat space will not be a good approximation. If we think about energies much smaller, we'll be talking about wavelengths which feel the radius of curvature. And so there's some range in between, and it's a very broad range, for which flat space is a good approximation. Okay, we are going to be mostly interested in the cosmic scale, because it's the cosmic scale which feels the de Sitter character of the geometry. Again, the microscale is the geometric mean of the maximum and minimum energy scale.
I have a question.
Yeah.
So what happens when you have multiple black holes? What does the geometry look like?
What happens when you have what? When you have what?
Multiple Nari black holes.
I have no idea. But in any case, we're talking about 2+1 dimensions where there are no black holes.
Okay.
I don't think you can have multiple Nari black holes, but as I said, this is not relevant for this talk. Okay, now there's a concept which I call the separation of scales. It's the fact that in the semi-classical limit, in which the entropy becomes infinite, the ratios of some of these scales diverges. For example, the maximum to the microscale diverges in the semi-classical limit. It's also equal to the ratio of the microscale to the minimum scale, and those go to infinity. That's the separation of scales. And in that limit, the various scales, in particular the microscale and the minimum scale, have physics associated with them which is kind of disconnected from each other. The Physics around the microscale is well approximated by flat space physics. Physics at the minimum energy scale, for that one has to keep track of the finite radius of curvature of the de Sitter space. There are, in a certain sense, different Hamiltonians and different dynamics describing physics at these scales, and that's going to be important to us. One assumption that I will make is that the string scale, we haven't defined the string scale yet, but the string scale in ratio to the microscale is finite. That's the analog in 4 dimensions of saying the string scale ratio with the Planck scale is finite. That's a usual thing that we do. We assume that the string scale is in some fixed proportion to the Planck scale, and I will assume that. Incidentally, that assumption is tantamount to what I'll call subcosmic locality. If we take the string scale to be a measure of the non-locality of the physics, then if the string scale is in fixed relationship to the microscale, it means in the semi-classical limit that the string scale becomes infinitely small on the cosmic scale. So we can call that subcosmic locality. It's the analog of sub-ADS locality in ADS. Okay, let's talk about now why DSSYK sub infinity. Why is that something we should be interested in this context? First of all, why SYK? Here I don't have anything very deep to say. It's simply by experience, we have seen close connections between JT gravity and SYK. That's all. That's it for why SYK. If we're talking about JT gravity in any form, experience has taught us that there's a good chance that the microscopic completion of this theory is SYK. This is something to explore. I don't say this is necessarily true. It's something to explore. It presents itself as something to think about. In particular, does the case with positive cosmological constant, is it represented by some kind of SYK physics? Something to try out, if you like. Why infinity? Why go to infinite temperatures? Okay, so that I think is most easily explained for a variety of reasons, but in this context, I think it's most easily explained by thinking about the Schwarzian boundary of SYK or of JT. Presumably that's where the degrees of freedom, the holographic degrees of freedom, are located. And this picture over here just shows the location of the Schwarzian boundary at different temperatures. At very, very low temperatures, the Schwarzian boundary is very close to the mathematical boundary of the anti-de Sitter space that is being represented. And as the temperature goes up, the Schwarzian boundary moves in toward the horizon. As I said earlier, the assumption about de Sitter space is that the holographic degrees of freedom live very, very close to the horizon. And so it's natural to increase the temperature until that Schwarzian boundary becomes very close to the horizon. Perhaps we could say until it becomes the stretched horizon, being a microscopic distance from the true mathematical horizon. That's one of many reasons why we would like to go to t equals infinity. It was the reason that I first proposed. There are deeper reasons that Edward and his colleagues have proposed, and other people. Temperature goes to infinity, and that's of course the same as saying that the entanglement spectrum is flat or the density matrix is maximally mixed. So that's the reason for going to infinity. But why DS? Why the double-scaled limit? Some people thought that I just got obsessed with the double-scaled limit because I like the sound of the term double-scaled. No, there's a serious reason, and I'm going to tell it to you now. In order to explain it, let me let me explain some of the dictionary between SYK and or the double-scaled SY, the double-scaled SYK and JT. First of all, the dictionary contains an L, which is the cosmic length scale, the length scale of the de Sitter space. The SYK version of that involves the parameter J, which we will come to. It's the fancy script J, which determines which has to do with the variance of the terms in the Hamiltonian. If you know what SYK, you know what script J is, or fancy J is. If you don't, well, it's not my business to teach it now. The mass scale associated with it is just the inverse. It's the Hawking temperature, and the Hawking temperature is equal to or proportional to the script J. And where does this come from? It comes from the study of quasi-normal modes. The quasi-normal modes of the SYK system, these are the quasi-normal modes associated with the fermions, have a frequency of order J. And by comparing the quasi-normal modes are, of course, frequencies on the scale of the cosmic time scale. And so by comparing quasi-normal modes, just roughly, the quasi-normal modes of the de Sitter space with the quasi-normal modes of the SYK system, one concludes that the cosmic length scale or the cosmic mass scale, the Hawking temperature, is proportional to J. The maximum length scale is n times bigger, where n is the number of species of fermions. That follows from something pretty classical. If you look carefully at the 2+1 dimensional theory, you will find that the maximum scale, again, that's the scale which shrinks the geometry by making the angular deficit equal to 2 pi. It's the entropy divided by L. That's on the gravitational side. Entropy is always going to be proportional to N, and L is inverse in J. And so the maximum mass scale is N times J. The microscopic scale, which is the geometric mean of these two, let's look at the mass scale, is the square root of N times J. That's the microscopic mass scale. It corresponds to a length scale, 1 over J times square root of N. And finally, we're going to discuss this. We'll come to it soon, the reason for it, but let me just state it now, that the string scale itself, excuse me, hold on, I've got it, okay. The analog of the string scale is Q times J. Hello. Just a moment. Okay, is Q times J. This we'll discuss at length soon enough. Let's just accept it for a moment that the string scale is Q times J. Okay, now let's look at the ratio of the string scale to the microscopic scale. This is the thing we would like to hold fixed. Square it. If you look up here at the microscale and the string scale, you will immediately find that that ratio is Q squared over N. And that's the lambda parameter of double-scaled SYK, Q squared over N. Holding fixed the ratio of the string to the microscopic scale is the double-scaled limit. That is the double-scaled limit, and that's the reason for being interested in the double-scaled limit. Not because double-scaled sounds like has a nice ring to it, but because it is holding fixed lambda. And strings, I'm writing this down again because it's important. And it also corresponds to subcosmic locality. The string scale and the microscale are in a fixed relationship to each other. So in the semi-classical limit, the string scale goes to 0 relative to the cosmic scale. That's the reason. That's the ultimate reason for wanting to be interested in the double scale limit, because of what I said. Any questions up till now?
Lenny, I want to ask you a question.
Mm-hmm.
Why is string scale 1 over QJ?
But we're going to discuss that.
Yeah, the reason I asked is that there are definitely better experts knowing this much better than me in the audience. Yeah. But I asked the people, and they told me that from the corrections of the Lyapunov exponent, it seems like the string scale has to do with temperature. That's just the words I heard. I mean, correct me. I'm sure.
I don't know what they're talking about. I don't know what they're talking about. I will tell you why. Incidentally, that's also the scale of chords, Q times J. And one of the themes I'm going to advocate is that chords, I distinguish between chords C-O-R-D-S and chords C-H-O-R-D-S. One of them has an H in it and one of them doesn't. And I'll tell you what I mean by it. The one with the H in it is the chord that corresponds to the operator equal to the Hamiltonian. I'm not interested in that one. I'm interested in C-O-R-D-S, which are any other chords, which correspond actually to matter in the geometry. So I will call those chords with C-O-R-D-S, and one of the themes that I'm going to advocate is that those chords are the analog of strings in higher dimensional theories. They behave like strings, or at least in some respects, they behave like strings. And my view is that chord theory is the natural analog of string theory in de Sitter space, but we'll come to that. Okay, let's talk about what we mean by DSSYK infinity, and I'm going to consider the complex version of it. The complex version of it means that the fermions are complex fermions, Q species of complex fermions, 2Q species of real fermions. The Hamiltonian, you've seen it before. It's a simple generalization of the Hamiltonian of the usual real SYK system. Each term contains Q antifermions and Q fermions. It has a set of parameters J. Those J's are drawn from a statistical Gaussian distribution with a variance J squared. And here is the variance. You may or may not recognize it, but here is the variance. It is slightly different than the usual convention. The usual convention has an extra factor of Q squared and 1 over Q squared in the denominator. And the difference has to do with what time scales we're working with. If we're working with the time scales associated with cosmology, then the appropriate Hamiltonian is, I think, Q times bigger than the Hamiltonian if we were working with the scales associated with chords or the string scale. Anyway, this is the Hamiltonian associated with cosmic. It's a question of time scales. When you rescale time, you rescale a Hamiltonian. It's kind of trivial. There's nothing important here. But if you're familiar with these things, you might say, what happened to the 1 over Q squared? Well, it's just a change of scale. Okay, so that's
just one clarification.
Yeah.
I mean, is lambda the Lyapunov exponent?
No.
The lambda that you.
No.
But is lambda dimensionless?
Q squared over n.
Yeah, but is it dimensionless?
Yes. Q is an integer, n is an integer. Yes, it's dimensionless.
Okay.
Yes, it is. Okay. Now, that's the definition of the theory we're talking about. We are, of course, going to be interested in the ensemble average, and I will think of that as a theory in its own right, the ensemble average, averaging over the ensemble of J's with this variance. I'm going to tell you some things about perturbation theory in this context. Perturbation theory means perturbation in the Hamiltonian itself. In the Lagrangian, there's a term in the Lagrangian which is quadratic chi dot chi, and the rest of the Hamiltonian can be thought of as perturbation. The vertices of the perturbation series, the vertices are simply the terms in the Hamiltonian here, and notice that each one has Q fermions and Q antifermions. Here they are. This is the case Q equals 3 incoming fermions and 3 outgoing fermions, or 3 incoming fermions and 3 incoming antifermions. We'll give that a weight J, and that's our basic vertices. The vertices also contain a dotted red line. The dotted red line is another thing that comes out of a vertex, and it's associated with the ensemble average in a sense that I'll explain in a moment. There are propagators. The fermion propagators in the infinite temperature limit are very simple. They're simply epsilon. Epsilon here means the thing which is +1 when the argument is greater than 1, -1 when the argument is less than 1. So the propagators are very simple, epsilon of T2 minus T1. The propagator associated with the red line is this variance factor here, NQ factorial over n to the Q times J squared. Times just squared. So that's the propagator associated with the dotted red lines here. And its purpose, integrating over the J's, integrating over the ensemble of J's, is basically just equivalent to putting another field. It's a peculiar field. It doesn't have any time dynamics, but nevertheless, it's just integrating out another degree of freedom in the ensemble average theory. For example, here's a diagram. Here's a diagram that we could compute. Incidentally, in these diagrams, I will always imagine integrating over the times involved. What this diagram means here, let's not worry about it. Let's just talk about how you calculate it. There's, first of all, a J squared coming from the two vertices. There is counting factors. These counting factors just correspond to the number of ways of picking Q fermions and Q antifermion modes out of N. Q, what is it? It's Q choose N or N choose Q. You know what I mean. It's just how many ways are there of choosing Q fermion modes out of a total of N. It's a good approximation to say that it's N to the Q over Q factorial, as long as Q is much less than N. So these are counting factors. And then there's the red line, the propagator from the red line. That's N Q factorial over N to the Q squared. Oh, incidentally, these are squared because of the fermions and the antifermions. In the real SYK theory, this wouldn't be squared. Okay, so that's what we have. And then we have an integral over the relative time between the two vertices. That integral is divergent because the propagators are time independent, except for this sign flip. They're just the epsilons. And so, and this infrared divergence here is going to be important to us. We're going to ask what fixes the infrared divergence. But in any case, if you work this out, it's just J squared N, and we're going to mainly, for the moment, be interested in the independence of these graphs. Okay, so this first graph is order N times an infrared divergent integral times J squared. Here's some more graphs. Graphs are, there's a subset of graphs which are called melonic. They're sort of leading graphs, leading contributions. This graph is melonic. melon stands for melon, looks like a watermelon. This graph is non-melonic. Okay, let's concentrate on this graph for a minute. We can also work it out. It now has 3 time integrations, the 4 time integrations altogether. There are 4 vertices, but let's keep one of them fixed and integrate over only relative times. There's an integral d3t, which is again infrared divergent. And then there's some counting factors, which I won't go into in length, and the red propagators. And if you work it out, you'll find out again, it is proportional to n. It has different q dependence. And again, it has an integral d3t. Main thing for the moment is that it has the same independence. So it's part of the leading behavior as a function of n. Now let's come to graph C. C is non-melonic. If you work it out, you'll find out that it's not of order n. It's down by 1 power of n. It has some non-trivial q dependence, j to the 4th, because again, there are 4 vertices, and again, an integral over time. The general structure of the expansion, which you can convince yourself of by just working out a variety of terms, the general structure of the expansion is as follows. The factor of n on the outside, that depends on what you're calculating. That's trivial. If we're calculating some kind of vacuum diagrams, then there's always an n on the outside. If we're calculating scattering problems, the independence on the outside here may be different. That's not interesting. The interesting thing is that it's a sum over little n of terms which are 1 over capital N to the little n power times polynomials in Q. These are infinite polynomials in Q, which has just the form that I've written here. So it's a large n expansion. N equals 0 corresponds to the melonic graphs. N equals 1, some new family of graphs, little n equals 2, some new family of graphs, and so forth. Each family of graphs is itself infinite, and we can imagine trying to sum them up and finding these PNs of Qs. Let me compare this now. Now, this is a very striking thing. This should impress you. Let's compare this with the 't Hooft expansion for gauge theories. First of all, the 't Hooft expansion for gauge theories is perturbation theory, and each term in the perturbation expansion is also infrared divergent. So the presence of infrared divergences is there both in the gauge theory and in the SYK theory that I've described. But what is the structure of the expansion? Again, let's define capital N in this case to be n Yang-Mills squared. Why is that? Well, the number of degrees of freedom in the Yang-Mills theory is n Yang-Mills squared, not n Yang-Mills. And if I'm going to compare that with the SYK system, where the number of degrees of freedom is just this n here, I want to make the number of degrees of freedom here to be n Yang-Mills squared. So n Yang-Mills squared and n will be the same thing. The 't Hooft expansion, again, is of the same form, an infinite polynomial for each little n, an infinite polynomial in the 't Hooft coupling constant. Here's the 't Hooft coupling constant. Alpha is g squared Yang-Mills times n Yang-Mills. An infinite polynomial, each term, an infinite polynomial in alpha, divided by capital N to the little n, where the n equals 0 term now is not melonic, it's the class of planar diagrams, or better yet, the class of diagrams on a sphere, a spherical topology. There's a correspondence. The correspondence between these two expansions, you may think it's just accident. I don't think it's accident. And we'll see that it plays a significant role. Q, here we are, Q is playing the role of alpha. Hold on. Q and alpha. Q is like alpha in this expansion. Lambda, which is Q squared over N in the SYK system, is very much like G Yang-Mills to the fourth, which is equal to alpha squared over N Yang-Mills squared. If I took the square root of this, it would be G Yang-Mills squared is equal to alpha over N Yang-Mills. That's familiar. I've just squared that relationship. These two are similar to each other. Holding fixed lambda would be like holding fixed G Yang-Mills, which is not something we usually do in studying gauge theories, but we're going to be interested in it. Okay, so here again is the correspondence. Lambda is like G Yang-Mills to the fourth. Q is like alpha, and N is like N Yang-Mills squared. With those correspondences, these two 1 over N expansions have exactly the same form. Here it is again. I write it down again. Lambda is like G Yang-Mills to the fourth. Q is like alpha, and N is like N Yang-Mills squared. All right, now let's think about the various limits we can take. I've plotted here for the Yang-Mills theory. I've plotted the square of the 't Hooft coupling constant against N Yang-Mills squared. Let's talk first about the 't Hooft limit. The 't Hooft limit, we hold the 't Hooft parameter, the 't Hooft coupling fixed, and we go to large N. In other words, we move upward along these vertical trajectories till we get to asymptotic limits. That's the 't Hooft limit. We can consider the strongly coupled 't Hooft limit, which means we go far out to the right, way out here, but still move vertically upward. That would correspond to the strongly coupled 't Hooft limit. There's another limit which we can take, which corresponds to moving along these radial lines here. Those radial lines mean alpha squared over N Yang-Mills squared, fixed ratio, and that corresponds to fixed value of the Yang-Mills coupling constant. That in ADS-CFT is the flat space limit. It's the flat space limit which has sub-ADS locality. So that flat space limit, again, it's a much more difficult limit. We understand much less about it than the 't Hooft limit, but it corresponds to holding fixed alpha over N Yang-Mills, and that's moving out in these directions here. What's the correspondence in the SYK system? 1 to 1. I've plotted Q squared over here. I've plotted N over here. The standard SYK system, the standard SYK rules are to hold Q fixed and let N go to infinity. That's moving upward along these vertical trajectories. We can again talk about the strongly coupled version of SYK. That would be large Q going way out here, but moving vertically. That's the standard SYK limit. It's like the 't Hooft limit. On the other hand, we can also talk about moving along these radial lines here, these lines of fixed slope. That corresponds to Q squared over N fixed. That's fixed lambda. So fixed lambda is very much like fixed G Yang-Mills squared. This is something I think has been missed in the literature, this close correspondence. And I do think it's more than important. I think it's central to the whole question of double scale theory. Okay, what about the string scale, which I'll also call in this context the chord scale without the H. What is the string scale in Yang-Mills theory? The string scale in Yang-Mills theory, I simply mean the infrared cutoff scale, the confinement scale, the scale at which flux tubes form, hadron masses, Hagedorn temperature. They're all the same scale. 150 or 200 MeV or something like that. And that is what I mean by the string scale in Yang mills. We could call it the flux tube formation scale if you didn't want to call it the string scale. One of the important things that it does is to resolve the infrared divergences. Well, let's talk about the infrared divergences that occur in the perturbation series for the SYK system. They were just these integrals over time, which were unsuppressed, infinite. Those are also resolved by summing diagrams. In this case, using the Schwinger-Dyson equations. This appears in technical literature. I didn't do this. I'm not sure who first did it. It may have been Kitaev. It might have been Stanford and Maldacena. I'm not sure. But the end result is that by summing diagrams, the let's call it the renormalized, I'm not sure renormalized is quite the right word, the corrected single particle propagator here is corrected. And in fact, a diagram like this goes from just being an integral over dt, goes to being an integral over dt over cosh squared qjt. There's a suppression at large time, 1 over cosh squared. Now, if you're familiar with this kind of thing, you may find this q here surprising. In usual conventions, there's no q here. The reason that the q is there is because of the change of time units in going to cosmic time units. That puts a q here. In cosmic time units, instead of the standard units, it's 1 over cosh squared qjt, and that integral is now finite. The integral is finite, and it's 1 over qj. The important thing here is that a time scale has been introduced. A time scale, a cutoff scale, which resolves the infrared divergences, and that time scale is 1 over qj. You can see it here, qjt, the new time scale, which is a sort of non-perturbative, I don't know, semi-perturbative, Schwinger-Dyson-esque scale. 1 over qj is the new time scale, and that is a scale I'm calling the string scale. As I said, it is also the scale to be associated with chords in the chord theory. All right, so let's take this graph A that I introduced before, which was an integral over t. It started out as nj squared integral over t, but now we replace the integral over t by the integral dt 1 over cosh squared, and we find out that it's infrared safe now, and instead of being infinite, it's nj over q. I simply set this integral here to 1 over qj, which it is. The infrared divergences are gone, but more important, a new time scale has occurred, has materialized out of summing an infinite family of melonic graphs. We'll call that new scale the string scale. The mass scale associated with it is q times j. The length scale or time scale is 1 over q times j. Now that we know that, and we have a good reason for saying that the string scale is 1 over qj, we can now come back to this m string over m micro squared, and in fact, it is exactly q squared over n, which is the lambda parameter of double-scaled SYK. Again, holding fixed the lambda parameter is the same as holding fixed the string scale in units of the microscopic scale. Now, that to me is an extremely striking fact. And Good. Okay, so let's now come to another issue. In Yang-Mills theory, there's confinement. Is there an analog of confinement in the SYK system? And I say, yes, there is. And let me first explain why it's necessary that a large number of degrees of freedom be confined, and also what it means for them to be confined. There are too many degrees of freedom for them all to be bulk degrees of freedom. The amount of entropy contained in the bulk is very, very small. One or two units of entropy in the bulk in de Sitter space. There's a huge amount of entropy near the horizon. That's the standard horizon entropy. There are too many degrees of freedom if they were all allowed to propagate into the bulk. Only a tiny fraction can propagate into the bulk. I'm not sure why this. My G is dangling. Yeah. There are too many degrees of freedom for them all to be able to propagate, and only a very, very, very tiny fraction of them should materialize as propagating fields in the bulk. The N fermions cannot all propagate into the bulk, and in fact, I would guess that none of them do. This was something that was actually pointed out to me a long time ago by Edward, that most of the degrees of freedom must be confined near the horizon or near the stretched horizon. That's what I mean by confined here. Does it have anything to do with Yang-Mills confinement? I think it does. But that can be saved for another lecture. Its detailed relationship with ordinary confinement. But I want to talk about the sense in which things are confined. Confined here will mean that they are not free to propagate into the bulk of the static patch. They are confined dynamically to live strictly very close to the horizon. All right, to understand that confinement phenomenon, let's talk about the symmetries of DSSYK infinity. Confinement is, of course, associated with symmetries. It's associated with the gauge symmetries. We say the things which are confined, the things which are not confined are the singlets in ordinary gauge theory. All right, what are the symmetries of complex DSSYK infinity? Well, first of all, because it's complex, it has a U1 symmetry. The U1 symmetry takes chi to e to the I theta chi, and that symmetry is associated with the bulk Maxwell degrees of freedom, which I will assume exist. Bulk Maxwell degrees of freedom, photons in the bulk, are associated with this U1 symmetry. We'll come back to that. There is also another symmetry. This bulk symmetry here, or this symmetry here, is an ordinary symmetry. Every single instance of the ensemble has that symmetry. On the other hand, there is a symmetry of the ensemble average theory. And I'm going to think of the ensemble average theory as itself a theory where you integrate over the J's. The symmetry of that theory is SUN, where N is the number of fermion species. What's the action of the group? The action of the group is every fermion species transforms by unitary matrices. Here, I won't try to say the words. I'll just write it out. Unitary matrices for every unitary matrix. So for every element of SUN, there's a symmetry or an operation on the chi's. That symmetry is what I'll call SUN. But we have to not only allow the chi's to transform under it, the fermions, but also the J's. The J's are the coefficients in the action. They also have indices, IJK, LMN. We have to allow those quantities to also transform under the gauge group, or under the. If we allow both of these things to transform, then the Hamiltonian is invariant under this SUN. Now, it's an unusual thing to let the coupling constants of a theory transform under a symmetry. That's not something we usually do. The reason we do it here is because, remember, we integrate over the J's. In this ensemble average theory, the J's are degrees of freedom that get integrated over just like any other degree of freedom. And when we integrate over them to get the ensemble theory is SUN invariant, but only by virtue of also letting the J's transform. For example, we can consider a graph now in which we don't close up the dotted red lines, in which the dotted red lines are external objects. Let's call them external particles, external objects. A graph like this with external dangling J's transforms because the J's themselves have transformation properties. And so this would transform under the SUN group as a thing with two sets of indices associated with the endpoints of the red lines. If we contract the red lines to form a diagram with no external red lines, then what we get is still has to be SUN invariant, but it's SUN invariant with no dangling dotted red lines. The same thing can be said, for example, if we think about the propagator of a single fermion. We can start out with dangling red lines here, where we don't contract the red lines. And then this object now has transformation properties associated with the external fermions, but also the external J's. So it's a tensor in SUN with a lot of indices. If we then contract the red lines, what's left over still is invariant under the SUN, or still transforms under the SUN, but transforms only by virtue of the transformation properties. In other words, it's a thing which only has external fermion lines and is still SUN invariant, and therefore has to be proportional to delta I prime. Okay, so there's a symmetry of the ensemble average theory, which is SUN. Analogous in some sense to the SUN of gauge theory, but let's not belabor that right now. Okay, let's take this diagram. Let's take this diagram right here. Let me tell you what its value is if it's calculated. Incidentally, we have to integrate over the times, but those infrared divergences are now resolved. What we get is simply J. What does that J correspond to? What is the meaning of it? It's not the mass of the particle. The mass of the particle is a thing which you think about as correlations in the vacuum. We're not in the vacuum, or vacuum meaning the ground state. We're not in the ground state. We're in a state of infinite temperature. The meaning of this quantity is actually the decay rate. The decay rate of a fermion, if we make a fermion excitation, that fermion excitation will decay by the fermion falling into the horizon. It's also associated with quasi-normal modes. The meaning of this J here is that the Green's function, the fermion Green's function, decays like e to the minus jt. That's the meaning of these kind of diagrams here. They represent decay rates. Imagine, if you like, imaginary masses, imaginary energies. This is what I mean by confinement, that the fermion correlation function is e to the minus jt. I will think of as confinement of the fermions. Now, why is it confinement? This J here is related to the cosmic time scale. You might think that this is telling us that the fermions can propagate into the bulk, but I'll show you now why that's not true. Okay. Here's the Penrose diagram, or a piece of the Penrose diagram associated with the static patch. A time scale, here's the PODE, a time scale, cosmic time scale of order L, of order j to the -1, means a unit hyperbolic angle here, one radian, one hyperbolic radian time on the PODE here. So for PODE time, that a time of order L is just this much time. But let's look at it near the horizon, the same time unit here. Let's look at it near the stretched horizon. Let's focus in on the region near the horizon. Here it is. And let's imagine a fluctuation in which in which a fermion is emitted and reabsorbed near the horizon. If it looks like e to the -jt, if that correlation function looks like e to the -jt, what it's telling us is that fermion never propagates more than a microscopic distance. This distance here is microscopic. How microscopic? It depends on where we put the stretched horizon. But if, for example, we put the stretched horizon at the string scale, then the distance that the fermion propagates away from the stretched horizon is microscopic, just equal to the string scale. I call that confinement. So if the correlation function decays like e to the -jt, that means the corresponding quantum never propagates more than a microscopic distance from the stretched horizon. Is that clear? If not, I will. Hello, anybody there?
Lenny, it's clear, but it depends on the interpretation that this is happening at the stretched horizon, of course.
Yes. Yes. That's right. We're making the assumption that the degrees of freedom live near a stretched horizon. The stretched horizon is a microscopic distance from the horizon. These are assumptions. And with those assumptions, e to the -jt, even though j corresponds to an inverse cosmological time scale, that corresponds to fluctuations which never get more than a microscopic distance from the horizon. This is something which I was misled about for a long time. I thought a thing like e to the -jt corresponds to propagating well into the bulk, but it doesn't. What does correspond to unconfined? What corresponds to unconfined is fluctuations which can propagate all the way deep into the bulk. Let's say, for example, that can propagate all the way to the PODE and back. It doesn't have to be that far, just a classical distance into the bulk. What kind of timescales correspond to unconfined degrees of freedom? Those are L times the logarithm of, I choose Q here because by assumption, I'm taking the distance from the stretched horizon to be of order the string scale. It's a microscopic distance. It doesn't matter whether it's Q, just some microscopic distance, Q, L log Q, which L is 1/j, and Q is of order square root of n. So apart from a factor of 1/2, this is 1/j log n. This log is the same log that appears in scrambling when we think of something being scrambled when it gets to the stretched horizon. This large log is associated with the closeness of the stretched horizon to the true horizon. The closer the stretched horizon is to the true horizon, the larger this log n will be. This log n is the difference between being confined and not confined. Gamma is a decay constant. It's the imaginary mass. For an unconfined degree of freedom, we would expect gamma to be less than or of order j over log n. Okay, so that defines what I mean by confinement. Confinement means stuck near the horizon. Deconfinement means propagating deep into the bulk. And it corresponds to an extra factor of 1 over log n in the gamma. We've seen that the fermions, which are in the fundamental of SUN, are confined. There was no log n for them. The decay rate for them was just j. They are, therefore, confined. Let's come to fermion pairs. Fermion pairs are clearly interesting for us. Fermion pair, now I mean, I could mean a fermion antifermion, or I could mean a pair of fermions or antifermions. For the antifermion fermion system, there are singlet operators. The singlet operators, singlets under SUN. Here's a singlet operator, chi bar I, chi I, and I'll put a 1 over square root of n there for normalization. That's the singlet operator. There are operators in the adjoint of SUN. Those correspond to a chi bar I, chi j with a summation convention here, sum over I and j, with Tij being traceless. That's something in the adjoint of SUN. And then if I take fermion, or fermion, or antifermion, there are things in the antisymmetric product of two fundamentals, which are also transformed non-trivially into SUN. The only thing which transforms trivially is the singlet. These others are non-trivial, in other words, they carry SUN quantum numbers. Let's consider the decay rate of these various possible kinds of fields, how their correlation functions decay with time. To compute it, we just have to calculate the imaginary part of certain energies. I'm not going to go deeply into that. I'm just going to tell you what the calculation is. Here's a fermion antifermion pair, I and I bar, making a possible transition to J and J bar. This is the simplest graph. This is the leading graph, which couples the fermions and antifermions. It's the leading graph. And here's another one of very similar character. But if you look carefully at it, you will see that that in the final state here, the two fermions, or the fermion and antifermions, have been interchanged. Here we have J, here we have J bar. So the two fermions are in the final state are interchanged with respect to each other. That's why there's a minus sign. This was pointed out to me by Juan, incidentally, that if you look at these two graphs, they're different. This has two incoming arrows. On this side, it's two outgoing arrows. This one is different. But whatever. The two graphs have an opposite sign. I had originally thought that they add. They don't. They also have a matrix character to them. This is I bar goes to J bar. In the space of I bar and J bar, there's a matrix here. In fact, this graph allows the left one here, allows any I bar to go to any J bar. So the matrix structure associated with it is ones everywhere. Any I bar can go to any J bar if you look carefully at the nature of the graph. On the other hand, this one is almost very similar except it doesn't allow any diagonal. It doesn't allow I bar to go to I bar. It only allows I bar to go to a different JJ bar. And so there are zeros. Whoops, this should be 0 over here. 0 along the main diagonal. As I said, this was something that was pointed out to me by one. They almost cancel, but they don't quite cancel because there's a Q here and a Q minus 1 here. And if you work out the matrix, it's very trivial to work it out. That's just adding these two matrices. What you get is J over N, something which is quite small as N gets large, times a matrix 1, 1, 1, 1 everywhere, and Q along the main diagonal. Now, you don't have to keep track of this. I'll tell you what the results are. We're interested in the eigenvalues of this matrix. The eigenvalues for the singlet and the adjoint states. The singlet corresponds to a column vector 1, 1, 1, 1, 1. That's psi bar I, psi I, summed over I. The adjoint is corresponds to entries which add up to 0 altogether, for example, 1 and minus 1. It could be chi bar 1, chi 1, minus chi bar 2, chi 2. That would be in the adjoint. Chi bar 1, chi 1, plus chi bar 2, with all sums. That's the singlet. And it's easy enough to compute the eigenvalues associated with these two vectors are both eigenvectors of this matrix. And their eigenvalues, including the numerical factor out here, the eigenvalues are J and 0. The adjoint has 0 in the large N limit. In the large N limit, the eigenvalue associated with the adjoint is 0. The eigenvalue associated with the singlet is J. Now, there are additional graphs. The additional graphs correspond to, if you like, self-energy insertions on the two fermions. This is I bar. We can correct, the self-energy on this one, or the self, it's not really, it's an imaginary energy, the decay rate. The self-energies of these two are also order J, in the same way as this J here. And in fact, if you add them up, the self-energies plus let's call it the interaction term, what you find is that the decay rate for the singlet is exactly 0, and the decay rate for the adjoint is J. In other words, these graphs shift the eigenvalues here by an amount which makes the singlet have 0 eigenvalue and the adjoint have eigenvalue J. Now, this is interesting because we've seen before that when the decay rate is of order J, that corresponds to something which is confined. The adjoint is confined, the singlet is not confined. In fact, the singlet is a little bit trivial. It has no decay rate at all. What
One
about
comment is that the singlet is a conserved charge?
Yeah. We're going to talk about that. There's a very trivial reason why this is true, and we didn't really have to go through this calculation to see this part of it. We did have to go through the calculation to see this one here. Okay, so what about the antisymmetric two fermion system again?
And isn't it going to be true that the adjoint is effectively two independent particles?
Yes, it is. Yes, it is.
The answer really should be what you would have gotten just from the one particle by itself.
Yeah, that's correct. It really is just two independent particles. That's absolutely correct. I was going to say it, but I thought you might get lost in the discussion. The same is true, incidentally, of the antisymmetric. Let's see. The antisymmetric product of two fermions. Where do I have it here? The adjoint is this way. Yeah, the same is true of the. Okay, so if we look at the correlation functions, the adjoint correlation function decays like e to the minus jt, confined. the singlet, as Juan pointed out, well, as I pointed out, is simply flat, doesn't decay at all. All right, now as I think Juan said, there's a trivial reason why the decay rate for the singlet is equal to 0. It's because the singlet operator, chi bar chi, I've taken the commutator here. That's just to symmetrize it. There's it's adding a constant to the operator, chi bar, commutator chi bar I, chi I. It's a standard thing to do to define a charge. You can just take chi bar chi if you like, and not worry about whether it's the commutator. This S here is related to the conserved U1 charge. In fact, it is the conserved U1 charge normalized with an extra 1 over square root of n. The U1 conserved charge is conserved, and therefore Q and likewise S is time independent. Its expectation value is time independent, and therefore the correlation function is completely flat. Now, I'm going to come back to that. It seems a little bit trivial. We can make it less trivial. We can make it much less trivial, which I will explain as we go along. But the conjecture from experience of making a few calculations of this kind is that SUN charge is confined. Only the singlets are free to propagate into the bulk. That's a conjecture which I don't know how to prove. But from the experience of calculating, I've calculated it up to four particle correlations. And it seems like the singlets are always unsuppressed, and the non-singlets are always confined. Okay, let's talk about the triviality of the singlet. The triviality of the singlet is just due to the fact that it's proportional to a conserved charge. Its correlation function is completely flat. This is related to the fact that photons don't have any independent dynamics in 1+1 dimensions, 1+1 in the JT theory. JT theory with U1 gauge symmetry, the photons are completely trivial. At least if you don't give them a mass, the massless photons are completely trivial. The dynamics are trivial in 1+1 dimensions. And that's another way of seeing that the correlation function is completely flat. We would like to have a more interesting structure. We would like to have a structure which has some dynamics and which is not confined. And the way to do that is to give the photon a little bit of mass by Higgsing it. Higgsing in a holographic theory means simply breaking the symmetry in the holographic Hamiltonian. We can break the symmetry, the U1 symmetry, in a variety of ways. They will all give a little mass to the photon and give it some non-trivial dynamics. I find the simplest way, which is most easy to work with, is just to take a term in the Hamiltonian, which is very similar to the usual terms. Instead of J, we have a K, but instead of having half fermions and half antifermions, take a term which is the product of 2Q fermions and another term which is the product of 2Q antifermions. This clearly breaks the symmetry of the U1 symmetry. It breaks it a lot. I'll explain why in a minute. But there are graphs associated with this, vertices associated with it, and the vertices have all of their lines either going out or coming in. The dotted blue line is associated with the ensemble average over K. We'll imagine an ensemble average over K as well as J. In terms of the symmetry breaking, each vertex changes the charge by 2q units, 2q fermions coming out. And that's a large amount of symmetry breaking. Each vertex changes the U1 charge by an amount 2q. We could imagine a much less severe breaking in which, for example, there was only in which delta Q was of order 1. Because the charge breaking is so large in this version of it here, you have to divide by Q to make it comparable to a symmetry breaking in which delta Q was of order 1. But this is something we can do. The ensemble average, or the fluctuation in K, is taken to be of the same kind as for J, except with an extra factor of 1 over Q. This is convention. This is convention. You don't have to put the 1 over Q there. You can work with it without it, but things have better limits if you put a 1 over Q there. I believe that 1 over Q is there in order to keep to compensate for the fact that delta Q is so large. Okay, now we can use these vertices to correct, which means correct for the symmetry breaking for the various correlators. For example, the correlator associated with fermion antifermions, the singlet correlator, for example, now has a new term. Here it is. It's got 2 Ks, and it has a 1 over J. The 1 over J comes from the fact that, well, it comes from this melon here. The melon has to be integrated over time, and integrating it over time gives us an extra 1 over J. I promise you that's correct. So the answer is K squared over J. This is the decay rate for the singlet in the presence of the symmetry breaking. G of t, meaning the correlation function of S of 0, is e to the minus K squared over J times t with this particular symmetry breaking. I would compare that with the photon-photon correlations in the JT de Sitter space when the photon has a little mass. If the photon has mass m, it's e to the minus, or mu, e to the minus mu squared L times t. It looks temptingly like this. Remember that L is 1 over J. L is the same as 1 over J. Mu is a measure of the symmetry breaking, and K is also so we can add to our dictionary that the shift in mass of the photon is like K, and of course, as always, L is 1 over J. Now the photon has some dynamics. We can calculate, as I said, well, I don't know how to calculate the whole correlation function, but I do know how to calculate the decay rate. Adele, my student Adele, has calculated in the bulk theory, in the JT gravity, he has calculated the singlet correlation function. And in fact, this is a logarithmic plot here. This is logarithm, a straight line, means, an exponential decay. It really does look very exponential with a little glitch over here. This glitch occurs at the time of order log n. That little glitch occurs, but it's a small glitch. It doesn't seem to mean very much. It's there. I would love to be able to reproduce it, but I think that's
I have a question about that glitch.
Yeah.
So is the bulk computation a 2-point function computation in the sitter?
Yes. I'll
so
tell you. Yeah.
So I would have thought that computation depends only on the proper time between the 2 points.
Well, it does. Yeah. Okay, good. But
okay, so I could put the proper times both at the center of the static patch, right?
No, yes, you can. You can. But what we're doing here is putting the okay, let me draw a picture.
I'm going to try to say that there shouldn't be any feature in the correlation.
Well,
because-
okay, let's talk about, hold on just a second. Let me,
Juan, I think the feature comes from the transformation from the proper time along the stretched horizon to the proper time measured in the ambient de Sitter space.
okay, let me tell you exactly where it comes from. Here's what we count.
That's fine, Lenny. Since we are over time, I accept Ed's explanation.
Okay, let me just explain it. We're talking about correlations between points close to the stretched horizon. Now, if the points are very close to each other, the important trajectories in calculating the correlator look like that. But if they're farther apart, there comes a point where the signal can bounce off the pode. It can bounce off the pode with light-like trajectories here. That's what creates this glitch here. I'll talk about it a little more in a minute.
That is suggesting that is the correlator analytic at this point or not?
No. Oh,
okay.
well, okay.
Okay.
Good.
Hold on.
That depends on that. Okay, if you literally take the stretched horizon to be a fixed distance from the horizon, then it's not analytic. If you imagine fuzzing it a little bit over where you locate the stretched horizon, then that glitch will get smoothed out.
Well, let's take it at the finite distance. So
fixed numerical distance.
Fixed numerical distance. So then the
Yeah.
correlator should depend only on the proper time between the 2 points. And that
Yes.
proper time is finite, right?
Yes.
Okay, so now given that the 2-point function in de Sitter does not depend, I mean, it's only dependent on the proper time, I could put
Yes.
these 2 points both at the center of de Sitter. And then if I put the 2 points at the center of de Sitter, I don't expect any non-analyticity as I.
Well, I think you do. I think you do.
Okay.
This has been carefully calculated by Adele. From just look, the point is here that the proper time between here and here goes to 0. Let me give another, let's see, we should have another picture here. No, we don't have another picture. Let me draw this a little more carefully so that.
Hi, Juan. This is Adele. Could I maybe offer an explanation that might be satisfying? So it is true that the correlation function is just a function of the proper time, but the proper time itself will be a function of, let's say in static patch coordinates, both the static patch time separation and say the separation in the local d-2 sphere, right?
Yeah.
And for early enough times, the line element will get a negative contribution, a time-like contribution from the time separation, but a positive space-like contribution from the angular separation.
Oh, so
at early times, these can compete.
Okay,
yes,
sorry.
yes. You have to sample over all
okay,
angles.
Sorry,
only
I thought the 2 points were at the same angle. Sorry.
No.
Good. Yeah, that's right. Yeah. That's right. This is integrating over that angle.
Okay, sorry. I thought they were at the same angle. Sorry.
Now I regard this glitch. I regard this glitch as a real smoking gun of the bulk geometry here. If it could be reproduced, that would be wonderful. It would really tell us that what does it come from? It comes from propagating into the bulk, bouncing off the pode, and propagating back out. It's the S wave. And that glitch, it seems to me, is really an important smoking gun, but difficult to even think about calculating. There's a worse reason about calculating it that, okay. Now, all of the correlation functions we're talking about are the real parts of correlation functions. The imaginary parts of the correlation functions are much better diagnostics of things. They really have to do with causality, not just correlation, but causality. And you can see that, for example, in the imaginary part of that same correlation function. Indeed, it has a glitch, but the glitch is not a small glitch. The glitch is a really very, very prominent feature. The problem is as I described last time, imaginary parts of things in the SYK system exactly vanish because they are expectation values of commutators in a density matrix, which is just the unit density matrix. They exactly vanish. We think we understand that a little bit. It has to do with a number of things that I talked about last time, but in order to reproduce the semi-classical physics, it is thought that you have to introduce a clock into the system. And introducing a clock into the system is, we don't really know how to do that. This is what Edward has talked about and what I talked about last time. So reproducing the imaginary part presents its own difficulties, which I don't know how to address right now. What I just said is the imaginary part of a correlation function is the expectation value of a commutator. If expectation values are simply traces, this exactly vanishes, but we think the right way to deal with this is to not think about the correlation function in the vacuum, but the correlation function in the presence of a clock. And that raises a question of how do you build a clock? You certainly don't want to build a clock from Hawking radiation. That sounds crazy. Hawking radiation is, Hawking radiation is not the thing that makes clocks in our world. What makes clocks? Things of order the string scale. Clocks are made out of strings. If particles are made out of strings and clocks are made out of particles, then clocks are made out of strings. Or let's put it this way: the energy scale associated with clocks, ordinary clocks, is the energy scale associated with the microscopic scale, the microscopic or string scale. For example, we can imagine a clock just being a single string, just a single closed string, for example, a single closed string which has energy levels rest frame energy levels proportional to the square root of the angular momentum, square root of an integer. We can imagine superposing different string states with phases like that and use them to create a semi-classical string clock. That's one way we might do it. Superposing them with e to the minus I times the mass would give us a forward-going clock, what I called a forward-going clock last time. With the opposite phase would give us a backward-going clock. And if we then fixed our gauge by saying there's a forward-going clock present, then one would hope to see the imaginary part. One would hope to see the imaginary part having a glitch. Very far from being able to do that. Let me just come back to this picture for a moment. How long can such a string last? Well, that depends on what limit we take. If we take a limit which corresponds, let's say, to the 't Hooft limit in gauge theory, that means going vertically upward, then in that limit, the string will not decay. The string will not decay. It will just correspond to a vanishing string coupling constant going up along these lines. Finite string coupling constant corresponds to going along these directions. Along these directions, the string coupling constant is 0, and therefore the string won't split, it won't decay if we go up along the strongly coupled 't Hooft limit. So if we were to study the strongly coupled, the very, very strongly coupled 't Hooft limit, I think these string-like clocks could last forever. On the other hand, if we go along the double-scaled direction or the flat space direction like this, then the string coupling constant is finite. Strings can decay, strings can split, join, decay, and then the clocks will not last forever. So it's kind of interesting. We can think of limits in which clocks can last forever, but they are these limits which are not the real limits corresponding to flat space sub-ADS locality. Same thing I think is true in SYK, except what are the strings? The strings, I think, are the chords. Let me just correct my chords, C-O-R-D-S. Not the ones associated with the Hamiltonian, but other chords. Chords and chords at t equals infinity. What do we know about them, the temperature? And I would say not very much. I don't think we understand the theory of chords at infinite temperature. What are chords? They are in-fermion systems with n of order q. They have energy of order q times j, which is what I've called the string scale. And I'll tell you one thing that I know about them, which I find interesting. If we go back to string theory and we look at the coupling between strings, the actual coupling between strings, it's the string coupling constant, which is the Yang-Mills coupling constant squared, which is like lambda to the 1/2. Remember, it was G Yang-Mills to the 4th, which was like lambda. All right, so if, for example, a simple string scattering, which would be proportional to G string squared, would be proportional to G Yang-Mills to the 4th in a Yang-Mills construction of strings. What about chord-chord interactions? Chord-chord interactions also have a coupling constant. And I am told, I don't know, I don't understand this fully myself. I am told that the coupling constant for the interaction of chords, the corresponding diagram in which two chords scatter off each other, is lambda, the lambda parameter, which is like G Yang-Mills to the 4th. So it does seem that there is a correspondence between chord interactions, chords in general, the chord mass scale, and the string scale of the Yang-Mills theory. That's about all I think I know about chords at infinite temperature. Why do I bring this up? Because if we are ultimately forced to think about clocks in order to reproduce the semi-classical limit, then in this theory, the natural thing to do is to build clocks out of chords. I don't know how to do that yet. I'm not even going to try to convince you that that's something that is likely to work out. I'll just leave it at that. That's about all I had to say, which was a lot. Oh boy, I've gone on for a long time.
Well, thank you, Lenny. We've had quite a few questions, but anyway.
Well, I'm happy with questions.
Yeah, let's open up for more questions.
I think I'll insist with the glitch issue. So if this theory was dual to JT gravity plus matter, right? I think we do not expect a glitch because in that case, there are no extra. Okay.
So as I said, I think the glitch is the real smoking gun that would tell us that there's a bulk geometry comparable to de Sitter space.
But is the conjecture that this is dual to JT gravity plus matter, or what is exactly the bulk that you think is dual to this model?
JT de Sitter space.
Okay, so in JT we don't expect a glitch.
Sorry, wait, how do you know? Whoa, we have to put JT. Oh, I think we do. Well, let's take the imaginary part. The imaginary part is the thing which has the really prominent glitch feature. Naively, we just get 0. We just get 0 because the correlation function is the trace of something. So in JT, in JT, you say in JT we don't expect
the leading classical, just quantum field theory in DS2, right? So in that approximation, I don't expect a glitch.
Really?
I guess it's crucial that Lenny. I guess it's crucial that Lenny was considering it was considering DS3.
No, we're thinking about the dimensional reduction of DS3, which means S-wave excitations. All right, there's our Penrose diagram.
Well, it's not quite the same. So it's considering S-wave, I think it's not quite the same.
Yeah, Lenny, and maybe one thing that's worth saying is this is not what is usually called de Sitter JT, because in that case you're expanding about Nari, and your dileton is sort of like the So in that case, matter is minimally coupled to the 2D metric.
Exactly.
We're considering a case where we expand about 3D de Sitter. So the dileton's always order 1. The dileton is the static patch radial coordinates, say. So the actions are not the ones that you would standardly call JT de Sitter plus matter. It's always dileton coupled in a significant way.
Yes.
So it's not just quantum fields in DS2. It's either you can think of it as quantum fields in DS2 coupled to a bulk dileton field, or you can think about it as the S-wave reduction of fields in DS3. But in both cases, it will differ significantly from what's usually called JT de Sitter. We're expanding about Nari, and the dileton is some constant value plus a small perturbation.
Okay, so I would suggest not calling it JT because it's misleading.
Whoa, I think it is exactly JT. It's a solution in which the dileton...
Well, you're free to call it whatever you want, but people conventionally call JT gravity is usually a theory where the matter is not coupled to the dileton in a significant way. But this is just a social convention. Of course, you're free to call it.
I see. Okay, well, all right. So, good. Let's define it to be the dimensional reduction of the three-dimensional theory.
But Lenny, from your logic, is it clear that it should be that rather than what Juan called JT? In other words, from your logic, is it clear you should expect this glitch?
Which part of the logic now? From the dimensional reduction of 3 dimensions? Yes.
Oh.
No, from the relation to SYK. So SYK, the ADS context.
Okay.
Matches formulas from ordinary.
Here's what I think. I think the semi-classical theory has a hidden clock in it. There's no. It has a hidden clock in it in the sense that we can't reproduce the semi-classical theory without that clock. So where is that clock? That clock is over here. What I'm guessing is that the glitch can be thought of as scattering off the clock. In order to see it, I think you have to have the clock. You certainly have to have the clock to see the imaginary part, which has the good, firm, strong glitch behavior, and you need the clock. The clock modifies the state of the system. It's no longer the maximally entangled state. It's the state with a clock present. I'm guessing that the glitch can be thought of as scattering off the impurity in the system, which corresponds to the presence of the clock. Is that correct? I don't really know, but I know that we won't get it without the clock.
Lenny, let me maybe ask you again. I think we were discussing the issue of D equals 2 versus D equals 3. Mm-hmm. It's the glitch is only there when you are considering DS3. But what's the logic that you say that?
Well, when you consider the S wave of DS3.
Oh yeah, S wave of DS3. But what's the reason that you choose DS3 instead of a 2D de Sitter, like in JT?
Sorry, I say that the JT de Sitter space that I'm thinking about is the dimensional reduction of three-dimensional theory.
But now we see that they are slightly different. I mean, if you do the calculation of correlator in JT, you will not see the glitch.
That's because JT is a funny theory in which you've arbitrarily said that the matter is uncoupled from the dileton. That I think is unrealistic. I don't think that makes sense, frankly. The matter should be coupled to the dileton, but it certainly is coupled to the dileton if you take the JT theory to be, by definition, the dimensional reduction of the three-dimensional theory. The only reason for taking the matter to be uncoupled to the dilaton is so that it makes it easy to calculate things, but they're not the right things. I would guess that the matter that would come from the SYK system, that matter is coupled to the dilaton.
Maybe one thing worth saying is that it depends on which higher dimensional saddle you're descending from and expanding about. It's a difference whether you're expanding about higher dimensional Narii or a higher dimensional empty de Sitter space. If you're expanding about a higher dimensional Narii, which is not what we're doing, the dilaton to a very good approximation will be a constant plus a perturbatively small piece, which is why it's usually said that the matter is not coupled to the dilaton, because it's just coupled to a constant.
What does this have to do with Narii? Are you talking about
the thing that people usually call de Sitter JT, which is where I think some of the objections are coming from, is a specific case where the higher dimensional saddle that you're expanding about is Narii. You're considering fluctuations to the Narii geometry. And in that case, the dilaton is a constant plus a small perturbation. And to leading order, the matter action, even though it couples to the dilaton's a constant, just factors out into some coupling.
Isn't the dilaton time dependent in
that? What is called the dilaton in that situation, because what we would call the dilaton is some constant plus a small perturbation, and that small perturbation is what's called the dilaton in the literature. So the time-like piece is that small perturbation to the constant.
I know, but it's time dependent, right?
Yeah, it's time dependent. So another thing worth pointing out.
Look, the static patch is not static.
Yeah, that's the exact reason why we consider what we've been calling JT gravity instead.
That's a crazy theory. It's a crazy theory. It's a crazy theory in which the static patch is not static. It has a dilaton which goes to infinity at time infinity. It has a dilaton which is proportional to time instead of radial coordinate. It doesn't have a static patch.
No, it does have a static patch, I think.
Who wrote this paper?
Which paper? The JT gravity with in 2 dimensions?
Well, the thing that you're calling
JT. The JT with matter is many pages, hundreds of papers. Right. I don't in the ADS case. But
yes, but it doesn't have a static patch. Is that correct?
No, it does. Yeah.
It does or does not?
It does.
Which is static?
Yes.
Static including the dilaton?
Well, it has 2 horizons. It has cosmological horizon and something you could call the black hole horizon. It's somewhat similar to the de Sitter space with a black hole, but yeah, that's so we're in 2 dimensions.
Well, I don't really, if you look at the JT equations of motion, let's say the Euclidean equations of motion, there's a dilaton field which could be,
I think I understand what you're saying. Yeah, so if you want the dilaton to be independent of the circle coordinate, then that's true. It grows it's time dependent.
Okay, so that theory in the Minkowski coordinates is not.
Yes, that's not the case I had in mind. So I thought for this discussion, you would have in mind the case that where the dilaton depends on the circle, but is time independent in the static patch. Well, the analog static patch.
So this, as you said, Juan, this is the static patch, which is similar to the Schwarzschild de Sitter static patch.
Exactly. Yeah, it's somewhat analogous to Schwarzschild de Sitter. Yeah, it's the 2-dimensional version of Schwarzschild de Sitter.
Well, let me come back to what I said in the beginning. The theory that we're talking about, the JT theory that we're talking about, where is it? Way back. Excuse me. A lot of transparencies. Wow. Okay. The theory that we're talking about is a theory that starts with 3-dimensional de Sitter space and then is dimensionally reduced on a circle. It gives rise to a theory with a metric, which is just a two-dimensional de Sitter metric, and a dilaton field, which is proportional to the radial coordinate r. That is a solution of the JT equations of motion with positive cosmological constant. That's the thing which I'm calling JT with a positive cosmological constant.
Yeah, I think I understand this. The only thing is that it's not very conventional. But
okay,
sociological statement, it's not a mathematical statement. So.
Oh, okay. It's the solution. It's the solution that has in the Minkowski framework a static patch, where the static patch is static.
Yes, I'm only objecting to the name. I'm
yes,
not
okay. We'll have to. Good. Yeah, I understand. It's not a good thing to change names. All right, so I'm happy to change the name of it. Do you have a suggestion? We can call it JT gravity with a static patch.
Truncation of
yeah.
I mean, this theory is singular at r equal to 0 because of the action for the scalar fields.
The theory is the r equals 0 is.
So from the two-dimensional point of view, r equal to 0 is some kind of wall, right? And the actions for
r equals r equals 0 is from the original point of view of the three-dimensional theory. It's a polar coordinate coordinate singularity.
Right. But since here we've gotten rid of the angle, now it becomes a somewhat singular point, at least the level of the description of this two-dimensional theory.
Yeah.
I mean, from the formulas you have in the transparency, it's not clear. But if you
it's true.
If you were to add the action of the scalar field of a matter scalar field, then it would be more clear.
I think it's a question of the boundary conditions at r equals 0. I think things are not particularly singular if you have Neumann boundary conditions. If you had Dirichlet boundary conditions, I think they would be quite singular. Neumann boundary conditions is what you inherit from the S wave of the three-dimensional theory.
Well, I think what I'm saying is that if you add the action of a scalar field in 3D and you dimension use it to 2D, then there will be in the action a term that is proportional to r. And then r equal to 0 would imply that the fluctuations of the scalars are very large. I mean, you can probably remove it by some coordinate redefinition and by field redefinition, and then you'll have a term, perhaps a mass-like term that goes like 1 over r. But this might be a detail, probably not important.
I don't think there's anything particularly sick about it. I think it is just the S wave of the three-dimensional theory.
And I understand how it's defined, and it's fine. I mean, you are free to consider the S wave of the 3D theory.
Yeah. Well, of course, the question in the end is which is the thing which actually corresponds to SYK system.
Sure. Yeah.
That's something that's probably too hard to answer right now.
I think it's correct to say that there is no evidence that this is the theory, right? Is there? What is the evidence that this is the theory? I mean, the glitch, for example, is not present.
I agree completely. The goal would be to see this glitch. To see the glitch, I think you have to have a clock. Certainly in the imaginary part, you have to have a clock, and the glitch is really prominent and a real feature of the imaginary part, and we don't know how to calculate that. So my point is this: here is a concrete proposal. It's a concrete proposal for the quantum mechanics, in which we can try to answer these questions. I think any version of this, any version of de Sitter holography is going to have the same kind of questions. It's going to have the vanishing of imaginary parts. It's going to have all the same questions. here is a case which we have a chance of trying to analyze. So why do I say that? Because we know a lot about the SYK system. So I make no claim whatever to have a strong piece of evidence that this is right. What I do claim is this is a concrete proposal which can be analyzed and which I think has many, many reasons to think that it may be connected with the Sitter space. Most of the reasons have to do with, well, you can call it dimensional analysis, scales, in particular, the existence of a string scale, the existence of, so all the things I described, I regard as evidence, but they're not the kind of sharp, detailed evidence that we would like to see by computing the glitch. So I make no claim to have proven anything. What I claim is that here's a setup in which you could try to analyze, and which I think has a good chance of seeing the glitch.
I don't see why the glitch is would be a small. Why is that the calculation we should do? So.
Well,
because suppose it's very powerful, I compute whatever thing with the double scale SYK, and let's say there is no glitch. Then the answer would be, okay, it's not this 3D gravity theory, it's maybe some other 2D gravity theory. In which
I'm not sure what you're calculating. We have to calculate it in the presence of a clock. Okay. I think that clock is important. We know that the imaginary part, which really has the significant glitch, that will just plain be zero without fixing the gauge to break the time reversal symmetry.
Mm-hmm. Right.
So so again, here's a concrete proposal. It has a set of excitations which potentially can be used to build a clock, and we can try to calculate correlation functions in the presence of the clock. I think I don't feel close to that, but I feel it's far away at the moment. But I think the point is that any holographic description of the Sitter space is going to face the same kind of problem. And so this may be the most tractable example.
Well, it sounds like we have our marching orders.
I certainly hope that somebody joins me in this quest, because I think it is extremely interesting and possibly important.
So anyway, I think I'm glad we've had this discussion at the end, which clarified better what some of the issues have been.
Good.
But in view of the hour, I think we should all thank Lenny. And
well, that's being in a state of some isolation. Sometimes a little bit difficult to realize what other people have been thinking, and in particular, this definition of what we mean by SYK de Sitter. Okay, I was unaware that there was another definition of it. So thank you.